next thing I want to do is talk about sets of linear transformations and the associated matrices to them. So we know from section 10.2, from proposition 2, the second part, that the set of F module homomorphisms from V to W is an F module. So what does it mean to be an F module? It means you're a vector space over F. So if V and W are vector spaces over F, what is an F module homomorphism between them? It's just a linear transformation. So the set of all linear transformations from V to W is itself a vector space over F. So we know that we can go from a linear transformation to a matrix. But to write down a matrix representing your linear transformation, you need to make a choice of basis for V and a choice of basis for W. So let's choose a basis B of V and a basis E of W. And now for each linear transformation phi from V to W, we get an m by n matrix with entries in F. This is this M, B, E, phi that we've been talking about in this lecture. And one natural kind of question to ask is, as we vary over all linear transformations, what is this set of matrices that we're getting? And the answer is all of them. So this is the content of theorem 10 in section 11.2, which says, let's say that V is a vector space over F of dimension n, and W is a vector space over F of dimension m with bases B and E respectively. Then the map that takes an F module homomorphism, that is a linear transformation phi, to the matrix MBE phi is an isomorphism of vector spaces. So one thing to emphasize is that B and E are fixed, and we're varying over all the choices of linear transformation. So if this is an isomorphism of vector spaces, that means there's a bijection of the elements on the two sides. So in particular, we get a bijection between the set of all linear transformations phi from V to W and the matrices associated to phi with respect to a fixed choice of bases B and E. So I'll pause and erase, and then we'll prove this theorem, that this really is an isomorphism of vector spaces. In order to start the proof, let's first name the elements of the bases B and E. B will be V1 up through Vn, E will be W1 up through Wm. So we have to show that this map we wrote down that takes a linear transformation to the matrix MBE phi is an F module isomorphism. So that means that it's F linear, injective, and surjective. So let's just do each piece. A linear transformation is determined by where it sends a basis, meaning if I tell you where a linear transformation sends a basis for V, then I tell you where it sends any vector in V. So if I give you a matrix, MBE phi, this matrix encodes where phi sends each element of the basis. So this map that takes a linear transformation to the corresponding matrix, MBE phi, is injective. That it's not possible for two different linear transformations to map to the same matrix, because if the matrix is the same, each column is the same. And if you send each basis vector to the same place, you send every vector to the same place. All right. Let's say M is an m by n matrix with entry alpha ij. We're just going to write down a linear transformation so that the matrix represented by that transformation with respect to the bases B and E is M. Well, there's unique linear transformation phi, where phi sends Vj, the jth element of this basis B, to the particular linear combination of basis elements of E, sum from I equals 1 to M of alpha ij times Wi. Why is that? Well, we've talked about this now a number of times, that you can send your basis elements anywhere you want, and then just extend the rest of, extend this map to be F linear by saying that, like, if I know where I send V1 and V2, then I know where I send V1 plus V2. And I know where I send any linear combination of V1 and V2. So because every element in V is a linear combination of your basis vectors, if you know where you send your basis vectors, you know the entire linear transformation. So if we make this particular choice of where to send the basis vectors, then this linear transformation has MBE phi equal to M. So this map is surjective because we started with a matrix and we wrote down a linear transformation that maps to it. This map is also F linear. Why? Well, it sends alpha times phi to the matrix where each column of MBE phi is scaled by alpha. And it sends the sum of two linear transformations to the sum of the corresponding matrices. Why is that? Well, think about what alpha times phi actually does to each vector. Alpha times phi of a vector v is alpha times phi of v, like the scalar alpha times the vector phi of v. So you have phi of v as a linear combination of your basis vectors w1 through wm, and you just scale each coefficient by alpha. And what does phi plus psi do to a vector v? Well, it sends it to phi of v plus psi of v. So the first column that keeps track of where this linear transformation sends v1, well, it'll be the sum of the first columns of each of these matrices. So Zillman and Foote say this in a slightly different way that I think sounds a little cryptic. I find it helpful to write this out. They just say that the columns of a matrix are determined by where phi sends a basis, and phi is F linear. So that makes this map F linear as well. But what's being described in here is really these two statements together. All right, so that finishes the proof. So I want to point something out, which is this isomorphism depended on a choice of bases, one for V and one for W. And if you make a different choice for your bases, the corresponding map is still an isomorphism, but it's a different isomorphism. So different choices of bases give different isomorphisms. There's no natural choice of isomorphism. There's no best choice. So it's just something to keep in mind that there are many, many, many isomorphisms between this space of linear transformations and this space of matrices. One last thing that I'd like to talk about in this video is that this result immediately tells you the dimension of this vector space of linear transformations. Because Hom F VW is isomorphic to this space of M by N matrices with entries in F, their dimensions have to be the same. And that dimension is the dimension of V times the dimension of W. So what's going on is this space and this space of matrices are isomorphic, so they have the same dimension. And the dimension of the space of matrices is easy to see, is M times